S. Chand presents educational video lectures as per the new UGC CBCS curriculum. Absolutely free. Difficult science concepts made easy. Study anywhere, anytime.
So we all know that we are surrounded by gases. But have you ever wondered that what are these gaseous molecules composed of? Can we have a look at the inside at how do these molecules behave at molecular level? Welcome to S. Chand Academy. Myself, Dr. Mamta Sethi. Today we will be discussing about the states of matter. To begin with, we will be starting with the most simplest state of matter, that is gases. For more details, you can refer to the book by S. Chand Publishing. Please click on the link given in the description box. To begin with, gases is the most simplest state of matter. Gases, we know that they do not have any fixed shape, they do not have any fixed volume. So they assume the volume of the entire available space, and most importantly that gases can be compressed to a smaller volume by the application of pressure. Then moving on to liquid state of the matter. Liquid state is, again, they do not have any fixed shape, they are flexible, they take the shape of the container, whichever container they are placed in, but liquids cannot be compressed the way gases can be compressed. Now coming down to the most ordered state of the matter, which is solid states. Solids, of course, we know that they are rigid, they have fixed shape, they have fixed volume, and how much ever pressure we may apply, we cannot compress the solids. So moving on to the gaseous state of the matter, we know that gases at molecular level, the most studied state of the matter. Out of all the states of the matter, a lot of study has been done on gaseous state. So to begin with, the gaseous state can be easily explained on the basis of a very famous theory which is called kinetic theory of gases. Now, kinetic theory of gases is a theoretical model which explains the behavior of gases at molecular level. Now, this theory is based on certain assumptions. So, let's move on to the first assumption. A gas is always composed of tiny particles. They can be atoms, they can be molecules, and these molecules are so small that the volume of individual molecule is negligible in comparison to the volume of the entire gas. We can assume that this is a container and the molecules of gas, they are just like point masses. Then the volume, we can see here that it is almost negligible in comparison to the total volume of the container. Then next is that in the absence of any external force, these particles, there are so many, there are not one particle, there are many gaseous particles which are present in a sample of gas, and these particles are constantly moving. They are constantly moving in random direction, and their motion follows the Newton's laws of mechanics, Newton's mechanics they follow. These molecules during the course of their action, they are moving in this direction, some of these they are moving in this direction, some may be moving in this direction. So during the course of their motion, they interact, or we can say that they collide with each other. Now when we say that they collide with each other, we must be curious to know that what kind of collision is this. This is elastic collision. So the gaseous molecules undergo collisions which are perfectly elastic in nature. Elastic in nature means that the momentum which has been lost by one molecule is exactly gained by the molecule which collides with it, and there is no net gain of momentum. Now in addition to these two assumptions, we have another assumption that these gaseous molecules are moving independently of each other. So this is the most important assumption of the kinetic theory of gases, which says that there are no intermolecular forces of attraction between the gaseous molecules. And of course, we all know gases, they have pressure. Now, what is the origin of this pressure? The pressure in the gases is due to the bombardment of these molecules with the walls. Now, they collide with each other also, and these molecules, they collide with the walls of the containers as well. Now, for calculating the pressure, the molecules which collide with the walls of the containers are only taken into consideration. So these are basically the assumption on the basis of which the behavior of gases has been explained. Now this was all about the qualitative description about the kinetic theory of gases. Now kinetic theory of gases can be easily interpreted in terms of this mathematical equation. Very briefly, I will be discussing the derivation of this particular equation, which we call kinetic gas equation. We call this as kinetic gas equation. So to begin with, we may assume there is a cubic container. The length of this cube is, let's say, L. A molecule of mass m is placed inside this. The container has a volume V that we have already understood in the assumption of the kinetic theory of gases, that this molecule, when it is during the course of its motion, it strikes with the wall of the container, it will count into the pressure term. So what happens, this molecule is having mass m, it moves with velocity u, therefore the momentum which it has, mu. Now after the collision with the wall, since we have already understood that the collision is perfectly elastic, therefore it would come back with minus u velocity, which is equal in magnitude but exactly opposite in sign. Therefore the momentum with which it will come back will be minus mu, and this is the net change in the momentum which this molecule will experience. Remember that this is only the motion of molecule along x direction. For the sake of simplicity, we will do these calculations for x direction first, and later on we can generalize it for all the three directions, and therefore the net change is going to be 2mu. Now since this molecule is moving with velocity u and covering distance L, therefore the time is length upon velocity, and this is going to be L by u. Now rate of change of momentum, delta px upon delta t, it is going to be 2mu divided by L by u, it is going to be 2mu square upon L, right? So this is going to be the rate of change of momentum along one direction. Now since we have calculated it for one direction, now we know that the motion of this molecule is not only restricted to x direction. So we will have to take the components of velocity along all the three directions, that is x, y and Z. So generalizing this expression in 3 dimension, we would be getting delta P upon delta T, that is rate of change of momentum, which is given by twice of mu square by L. The component of velocity along y direction will be v square v, so it is 2mv square, length remains the same. The component of velocity along z direction is going to be w, so w square upon length remains same, and this we can write together twice of m c square divided by L. So this is the net change of momentum, which we can say that it is the change of momentum when a molecule undergoes motion along all the 3 directions. Now, since we know that there is not one molecule here which is undergoing collision, a gas is composed of let us say even if there is 1 mole of gas, it is composed of Avogadro number of molecules. So taking into consideration all the molecules which are undergoing the collision, we would be taking the sum of these molecules, summation of velocities for all molecules. So taking summation over n molecules, then our rate of change of momentum will be given by summation from 1 to n is the total number of molecules, twice of m by L. Now this is, so Ci is the velocity of ith molecule. Now we may define the mean square velocity as in we can take this twice of m by L common, since mass is constant. So the only variable that we would be having here will be velocity Ci square. Now multiplying and divide by n, we will be having now this term can be defined as mean square velocity, and therefore we can write rate of change of momentum will be equal to twice of m by L and then n, and this is your mean square velocity. Now that we have calculated the rate of change of momentum, now we all know that what do we mean by the term rate of change of momentum. As per classical laws of motion, this is defined as force. And what is pressure? How is pressure related to the force? Pressure is given by force upon area. Force per unit area is called as pressure. So we have already calculated the pressure, which is given by twice of m by L, n and c square, dividing this with the area. So area of the surface area of the cube is given by 6L square, and we also know that L square into L, which is L cube, becomes the volume of the cube. So it is going to be twice of m n c square divided by 6v. So what is the final expression that we are having? It is 1 by 3 m n c square. So this is the divided by v also. So this is the pressure which is exerted by gaseous molecules which is having mass m. There are n molecule, v is the volume and c square is the mean square velocity. This equation can be rewritten, and you are, I think, most familiar with this equation, which is taking volume on left hand side, we get 1 by 3 mnc, and this is the most famous equation, which is quantitative representation of kinetic theory of gases, which is your kinetic gas equation. What is the significance of obtaining this equation is that most of the properties of the gases, most of the laws, we know that Boyle's law, Charles' law, Avogadro's law, Dalton's law of partial pressure, these all laws can be derived using this kinetic gas equation. But I am not going to derive all those laws, but we are going to just use it as such that this is the mathematical form of the kinetic theory of gases. So, after having understood the quantitative as well as qualitative description about the kinetic theory of gases, it then becomes important for us to explain the behavior of ideal gases. As I mentioned in the earlier slide, that kinetic gas equation can be used to derive Boyle's law, Charles' law, Avogadro laws, and many more laws which explains the behavior of gases. Now, combining all these laws, now we all know that how do we define Boyle's law. So, we know Boyle's law, which says that volume of a gas is inversely proportional to pressure at constant temperature and number of moles. So, number of moles and temperature has to be kept constant. Next is that again, how is volume related to temperature? At constant pressure and for a constant number of moles, volume is directly proportional to temperature, which is nothing but Charles' law. And at constant temperature and pressure, how is volume related to number of moles? It is directly proportional to N. Now, combining all these three laws, we can write that volume is what? It is directly proportional to number of moles, temperature, and is inversely proportional to pressure. When we remove this proportionality, we put a constant here which is called as R, and rewriting this equation, we get this famous equation, and this is known as nothing but ideal gas equation. Now, this equation is valid for all the ideal gases. It becomes here important to understand that what is the value of this constant. So, R, which we are writing from the equation, that is PV is equals to nRT, R becomes equal to PV upon NT at normal temperature and pressure, which are the conditions at which pressure is 1 atm, temperature is 0 degrees Celsius, or you may call it 273.15 Kelvin. For 1 mole of a gas, the volume which a gas occupies at NTP is always a fixed number, which is equal to 22.414 decimeter cube. The value of R comes out to be 0.8206 decimeter cube atm per Kelvin per mole. In SI unit, what is the difference? The difference will be only when the pressure in atm is expressed in newtons per meter square. In SI unit, this is the relationship which pressure has between 1 atm and Newton per meter square. So, substituting the value of the pressure in Newton per meter square, we get the value of R. So, depending upon the rest of the units, wherever we want to use the value of R, R is known as gas constant. So, this is a very important constant. In many of the physical chemistry problems, we need to use the value of R. So, we have to be vigilant, we have to be very careful about the units of R, that which value is to be inserted. So now that we have understood about the behavior of ideal gases, so let us here take a small break. So in the next session, we will be basically discussing about whether this equation is always followed by all the gases or under a certain conditions of temperature and pressure. So what exactly is the behavior of gases in real scenario. So that is what something which we are going to learn in the next session of this lecture.
Hello everyone, I am Dr. Seema Thakran. Welcome to S. Chand Academy. I will be teaching you topics limit and continuity, differentiability, partial differentiation, tangents and normals, curvature, curve tracing and many more. Please like, share and subscribe S. Chand Academy and don't forget to press the bell icon for the future updates.
So welcome back to S. Chand Academy. Before moving on to the break, I had asked you the question that whether this equation, which is PV is equals to nRT, the ideal gas equation, is obeyed by the gases under all conditions. So as we know that ideal remains ideal only. No? So real gases in real scenario, they would hardly show the ideal behavior. Even if they show only under specific conditions of temperature and pressure. Like we know that real gases, they also tend to, what do we mean by real gases? The gases which do not obey this equation. The gases which obey ideal gas equation under all conditions of temperature and pressure are known as ideal gases, and the gases which do not obey this equation are called either real gases or non-ideal gases. Now the quantitative expression for the deviation from the ideal behavior. Now if we say that they do not behave ideally under all conditions of temperature and pressure, so that means they deviate from ideal behavior. But how much deviation is there? So that is given by this expression which is known as compressibility factor. Now this factor is defined as the ratio of the product of pressure and volume for the non-ideal gases to the product of pressure and volume for the ideal gases, which may be further written as PV upon nRT using ideal gas equation. And since V upon N, what is V upon N? Is volume of 1 mole of a gas. So we may further write this equation is compressibility factor as PVM upon RT. Now what does this? We understand from this equation that for an ideal gas, this product will be always equal to the product which is valid for ideal gases. Therefore, the ratio becomes 1. So Z, which is compressibility factor, will always have a value 1 for ideal gases. But as I told you that they do not tend to behave ideally, so obviously they deviate. So when they deviate, the value of Z will also deviate from 1. So it can be either less than 1 or it can be greater than 1. Now what is exactly the meaning of Z greater than 1 or less than 1? What is the physical significance of the value of compressibility factor? That can be easily understood with the help of these compressibility curves. So we can see that what are these compressibility curves? These are basically Z versus P plots. So we plot compressibility factor versus pressure, and as we can see here, this line, this horizontal line represents the behavior of ideal gases. This represents the value of Z equal to 1. So this is for ideal gases, but we see that most of the gases with which we are familiar, that is ammonia, carbon dioxide, methane, hydrogen, helium, all these gases, none of these gases are having Z equal to 1. It means that they do not behave ideally under all conditions of temperature and pressure. Now, as we can see on the x-axis, pressure is there. So, pressure is 0 atm here and roughly about 100 atm, 200 atm, 300 atm, 400 and so on. So, pressure is increasing on x-axis. So, we can see that for a pressure close to 0 atm, all gases will have Z equal to 1. So, when the pressure is low as in 0 atm, all gases tend to behave ideally. They will have Z equal to 1. But as the pressure increases, what happens? That they tend to show deviation from the ideal behavior. Now, we can see here that there is two types of deviation which these gases show. For, let's say, for ammonia, carbon dioxide and methane, we can see that the value of Z first decreases, it reaches a minimum and then again it starts increasing. So, these are the gases which we can also correlate are the gases which are highly soluble, which these gases can be easily liquefied. So, we can make a generalization also that the gases which are easily liquefiable and soluble, they tend to show more deviation from the ideal behavior, right. So, this is what, as pressure increases, the value of Z becomes lesser than 1, reaches a minimum value at an intermediate pressure, and at a high pressure, as we can see, all these gases, they have Z greater than 1. Now, what is the meaning of greater than 1? So, when Z is greater than 1, it means the numerator is greater than the denominator. So, PV is greater than PV ideal. So, it means the volume which a real gas occupies is more than the volume for an ideal gas. It means the volume which is available for compression is quite less compared to the ideal gas. So, these gases are basically in this region, at high pressure region, the gases are less compressible. Why are they less compressible? Why do they, they can't be easily compressed? It is simply because of the reason that under high pressure, what happens at high pressure? If you apply pressure, gases will compress and they will, squeeze down to a lesser volume. Under the condition of lesser volume, the molecules of gas will come close to each other. When they will come close to each other and they are so close to each other that at that point what happens, that short term repulsive forces. So, what happens? Short term repulsive forces will come into play. So, at short distance, always remember a thumb rule. At short distance, repulsive forces dominate, and at a larger distance, attractive potential or attractive forces dominate. So, when the molecules of gas, they experience repulsive forces, obviously it would be difficult to compress, and hence the compressibility factor for these gases would be greater than 1. What happens at intermediate pressure? Not pressure as low as 0 atm, but I am talking about intermediate pressure. So, we see that gases show a dip. So, this dip is because of the fact that gases at this point of time or maybe at this pressure are more compressible. Why? The reason I have already explained you is because of the more dominating attractive forces between the gaseous molecules, and therefore this kind of behavior is shown. Now, you must be wondering that why this behavior like dip in the curve is not shown by hydrogen and helium. It is because of the fact that these curves have been plotted at 0 degrees Celsius. all these compressibility curves have been plotted at 0 degree Celsius. Now, the temperature which is required for hydrogen and helium to convert into gases is quite low. So, if we somehow are able to decrease the temperature up to minus 165 degrees Celsius for hydrogen and for helium minus 240 degrees Celsius, even hydrogen and helium, they would also be showing the similar kind of trend. So, since this temperature 0 degrees Celsius is much above the temperature which is required for hydrogen and helium to convert into the liquid state, therefore, hydrogen and helium will always have Z greater than 1, and that is the reason why they are also called as permanent gases. So, these are the gases which can be easily liquefiable, more deviation, more liquefiable and more soluble. But hydrogen and helium, since this temperature is not quite easily achievable, therefore these gases would always remain as gases under the normal conditions of temperature and pressure. Now let us try to understand the effect of temperature. So compressibility curves we have already plotted, and we have seen that gases, how do they behave at low pressure, intermediate pressure and at high pressure. Now we have the earlier plot was for different gases at one temperature. Now in order to see the effect of temperature on these curves, what we have done, we have tried to plot these curves for one gas but at different temperatures. So these curves, as we can see that the curve which is showing dip here has been plotted at 200 Kelvin, and the yellow line which is showing almost no dip has been plotted at 1000 Kelvin. So it is very clear from these curves that as we keep on increasing the temperature from 200 Kelvin to 500 Kelvin to 1000 Kelvin, the dip means what? Dip indicates the deviation from the ideal behavior. So as we keep on increasing the temperature, the dip in the curve also decreases, and there will come a temperature where this particular dip will completely disappear, and the line, means this line will become parallel to the x-axis. This is the point where PV, what does this indicate? It indicates Z is equal to 1. It means the product of pressure and volume becomes constant here. Now if the product becomes constant here, it means that this is, what is this? This is the alternative form of Boyle's law, right? Alternative form of Boyle's law. It means that at this point, at an elevated temperature, the gases, for an appreciable range of pressure, see, from let us say 0 to 200, we can see that the line is almost parallel to the x-axis. So for this region, the product of pressure and volume remains constant. So it means that under these conditions, at elevated temperature, for an appreciable or considerable range of pressure, gases obey Boyle's law, or in other words, we may say that gases tend to behave ideally. Now if this obey Boyle's law, so this temperature will be different from different gases, for different gases. So how do we define? We define this temperature as Boyle's temperature. What do we call it? We call it Boyle's temperature. So what is Boyle's temperature if somebody asks you to define it? It is the temperature at which the gases obey Boyle's law for a considerable range of pressure. Now what happens below this temperature and what happens above this temperature? Below this temperature, gases tend to behave, this kind of dip will be observed. What is this dip? is that with the increase of pressure, there will be deviation, z's value of the z will decrease, will attain a minimum value, and then again it will start increasing. And the opposite trend, if z is greater than 1, z is greater than 1 for Boyle's temperature. Boyle's temperature is denoted by TB. So above Boyle's temperature, all the gases, they will have Z always greater than 1. So the value of compressibility factor for these gases will always be greater than 1 above Boyle's temperature. So this was all about the gases, the ideal gas equation, how gases deviate from ideal behavior. So we have sort of come to a conclusion where we now understand that gases do not always behave in an ideal manner. But at this point of time, it becomes important for us to understand that what makes these gases to behave in a non-ideal manner. So what went wrong actually? It means we have to go back to the basic assumptions of the kinetic theory of gases, and we really have to see that whether all those postulates or assumptions that we had considered in kinetic theory of gases, were they actually true, or there is something wrong with those postulates. So when we go back to the postulates of kinetic theory of gases and try to analyze the behavior of gases, we find these two basic assumptions slightly not applicable to the ideal gases under all conditions of the temperature and pressure. So you might be wondering that I am repeating under these conditions of under certain conditions of temperature and pressure, because the temperature and pressure they play a significant role in defining whether the gases would behave ideally or in a non-ideal behavior. Now you see that this postulate says that the volume occupied by a single molecule is negligible in comparison to the volume of the whole container. Now you see, look at this, again I will draw this structure in which a single molecule is placed in a big container. Now according to the kinetic theory of gases, these molecules are what? These are point masses. So they are so small. So maybe you can at higher temperature, when the temperature is high, volume is also high, and when pressure is low, again the volume is high. Therefore what happens, that this volume becomes so small that it can be safely ignored in comparison to the volume of the entire gas or entire container. But what happens if we increase the pressure? If we increase the pressure, this volume might reduce to this small volume, and the same phenomena is observed at lower temperature. So if you lower the temperature and increase the pressure, the volume of the gas reduces. If it reduces at this, now compare the two volumes. So maybe compared to this big volume, this one molecule, the size of one molecule can be ignored, but the mass of this molecule cannot be ignored in comparison to the total volume of the gas at lower temperature and high pressure. So that means this particular assumption is not applicable under all conditions. The same thing we can understand in terms of forces of attraction. We did discuss in kinetic theory of gases that these gaseous molecules, there are so many molecules. So we said that they are moving independently of each other. They are not interacting with each other. There are no forces which exist between these molecules. Again, the same thing might be applicable when the volume is large, at low temperature, high pressure. But when we squeeze the gas, so when gaseous molecules are squeezed to a smaller volume by the application of pressure or lowering the temperature, what will happen? These molecules, they will come sufficiently close to each other that at this point of time the intermolecular forces of attraction cannot be ignored. So these are two basic assumptions of kinetic theory of gases which are wrong, which went wrong and led to the reason that gases deviate from ideal behavior. So it means that if we have understood that this is the reason why real gases behave differently from ideal gases, then that means we need to modify the equation. We have already, on the basis of kinetic theory of gases, we have defined this equation which is your ideal gas equation. Now if I am saying that my gases do not behave in an ideal manner, then obviously I cannot use this equation for non-ideal gases. So it means we need to modify this equation. So how do we modify that equation? That we are going to learn here. So we have understood that there was a problem in two assumptions. One was with the volume and another was with the forces of attraction, and therefore we need to incorporate some correction factors, and so that the new equation, the modified equation, we can use for non-ideal gases. So here at this point of time, van der Waals is a very famous renowned scientist who tried to study the behavior of real gases, and he came up with an idea, and he completely rejected the idea of treating gaseous molecules as point charges. He said no, the gaseous molecules are not point charges, they have definite mass, they have certain diameter which cannot be ignored, and therefore what we see that gases are highly compressible. In the very first slide we discussed the behavior of gases, that gases are compressible and they can be compressed to zero volume, which is not true, of course, because the moment these gaseous molecules, you apply high pressure, these gaseous molecules, they'll come close to each other. Now when they come close to each other and touch each other, they are hard spheres. Van der Waals introduced the idea of using or treating these gaseous molecules as hard spheres which have definite volume. So these molecules cannot penetrate each other. So that means this much of volume is not available for compression. So it means that the volume that we were assuming is slightly what? It is higher than what it should be. Therefore, we need to subtract a certain volume from the volume of an ideal gas, and which is here given by NV. So what is this known as? This is known as volume correction factor. This particular volume, which is your B, is known as excluded volume. This is known as excluded volume. So this much volume has to be excluded from the volume of the ideal gas in order to get the actual volume which is available for compression. So V minus NB. Similarly, pressure correction. So for understanding the the effect of pressure and how we need to change the value of the pressure, we need to understand that the molecule which is in the bulk is experiencing forces from all the sides, right? Now compare it with the molecule which is at the wall. Now this molecule is experiencing forces only from left hand side. It is not experienced. So net force here is not zero. So here the forces are what? Unbalanced. So this molecule is experiencing unbalanced forces. So that means it is not going to strike the wall of the container with the same force as it would have been in the absence of the forces which are pulling it or dragging it in the backward direction. So that means it is striking the wall but with slightly lesser pressure. So it means that the pressure which we were taking into consideration is slightly less than what it should have been. So therefore, we need to introduce or we need to add some pressure correction term to the already existing pressure, and which is now the force with which, now where do this this factor A n square upon V square comes from? This comes from the idea that there are two factors upon which the pressure depends. It depends on the number of molecules striking the wall, and it depends upon the force with which the molecules strike the wall. Both these factors are proportional to density. So this pressure correction term becomes proportional to square of the density, and density we know is inversely proportional to, here we are talking about number density. So n square upon V square. Removing this proportionality sign, we can write that pressure is equal to A n square by V square. So we have now understood that how much volume is to be subtracted, how much pressure is to be added. The next and the final step is incorporating these correction terms into the ideal gas equation. When we incorporate our corrected pressure and volume into this expression, we would be getting this expression which is known as van der Waals gas equation, and this is the equation which can be safely applied to all the non-ideal gases. So in today's lecture we have understood the the kinetic theory of gases, we have understood the behavior of ideal gases, and we have also understood the fact that under what conditions of temperature and pressure the gases behave ideally, and what leads to the deviation from the ideal behavior. And finally, we have derived an equation which is applicable to the non-ideal or real gases as well. So in the next lecture, we would be discussing more about ideal gases, about their velocity distribution, etc. So if you want to read in details about the topic, you can refer to the book by S. Chand Publishing, the link to which is given in the description box. Kindly like, share and subscribe, and do not forget to press the bell icon. Thank you.
All rights reserved. This video has been prepared for educational purposes only. No part of it may be reproduced or copied without the permission of the copyright holder.